Hello everyone, I am Tanu Banerjee, Faculty of Physics at Chinta. So today we are going to learn about a new topic, that is motion in two dimension. And in this topic, we will understand about how motion in two dimension works for uniform circular motion and non-uniform circular motion. This topic is very important for all the competitive exams like IIT and for the Physics Olympiad programs also, like NSEP, USAPHO, F=MA exams and International Physics Olympiad. We will understand that how the rotation of Sun and Earth in this toy model that we have created in our virtual platform will help to understand the centripetal acceleration and how centripetal acceleration is important to understand the revolution of the Earth around the Sun. So for the motion in two dimension, we have taken a Sun-Earth system in which we see first that when Earth is moving around Sun in a circular orbit, let's say for now, we are not considering the elliptical orbit, and how the acceleration and the velocity vector changes with respect to time, and then we will change some magnitudes in which we will see some parameters and it will be non-uniform in understanding. Okay, so let's see. So for this Sun-Earth system, as you can see, that this velocity that this arrow is showing, 17.98 meters per second, this is a constant tangential velocity. So velocity is constant for a uniform circular motion. So when we see that velocity is constant in a uniform circular motion, there is a parameter of acceleration that will be acting at the center towards the Sun. So this will give us a centripetal acceleration which is responsible for only change in the direction of the Earth, not the change in the magnitude. However, if we see and if we change the parameter, suppose if I turn on some other parameters, and we see that magnitude is changing. So this magnitude will turn it into an elliptical orbit. So here there are two parameters of acceleration. One is acting towards the tangent of the velocity vector. So acceleration that is acting toward the tangent of the velocity vector is increasing and decreasing its value as it coming closer to the Sun and going farther away from the Sun. However, if we change this parameter, it will turn into an elliptical orbit. For now, it's a aphelion and the perihelion state. You can see that the orbit has maximum velocity, and when it's going farther from the Sun, it has minimum velocity. So this is a tangential acceleration, and it is called non-uniform motion. And the acceleration that is only responsible for the change in direction is the centripetal acceleration, that is uniform motion. So now what happens if Sun suddenly disappears? As we see that for the Sun-Earth system, the only thing that is actually making it bounded to the orbit is the centripetal acceleration and the balance between centripetal acceleration and the velocity. So if Sun suddenly disappears, let's say we disappear the Sun, okay? Let's disappear the Sun. See, when we suddenly disappear the Sun, the Earth moves tangential to its orbit. So the only factor that is responsible for moving its tangential direction is the velocity that is acting towards its tangent. So here we can see that the factor that is responsible for its boundedness of the system, that is the Sun in its gravity. So here the centripetal acceleration is provided by the Sun's gravity. So the necessary centripetal force that is provided is Sun's own gravity. So if the Sun's gravity is not acting here, then certainly it will go in its direction wherever. From that we can see that it's follow a tangential path, and it will go forever in a straight line motion. So this in combination prepare a one-dimension motion when the Sun gravity is not acting on it, and a two-dimension motion when Sun is actually there and the gravity is pulling the Earth toward itself and creating a bounded system, which is negative g m1 m2 by r square. So now we will going to see that how centripetal acceleration and tangential velocity is related with the formula that we already know, that acceleration centripetal is equal to v square by r. So let's see. So let's draw a circle, okay, and let's take two velocity. So for this is we are doing for uniform circular motion. So if we see that this is the radial vector that is moving outward towards the radius, and this angle making theta, and this is the displacement that is followed, delta s, let's say. And there is two tangential velocity component. Let's say, for example, as the circular motion is uniform, so we can say that V1 is equal to V2. So V1 is equal to V2 is equal to V. Now if we move this vector component, as intuitively you can say that as the theta rotates and we fix it here, so we get this angle. These two angles we can solve with the help of similar triangles. So with the help of similar triangles, we can show that how acceleration and velocity are related. So here we see that these two triangles, as we see, will have same angle. So in rotation, when objects move by same theta, these vectors that is actually perpendicular to this radius of the circle would also make an equal angle, that is theta. Okay, and we can prove it with the help of by making two parallel lines and making it a transversal. So let's say these two values are being r, these two triangles will be isosceles, and as we know that V1 and V2 will be equal, so we can say that delta S, and this change in velocity would be delta V. So delta S by delta V, as these two triangles are similar, we can say will be equal to R times V. Okay, so delta S can be written as delta V times R by V. Correct? So if we take the derivative with respect to time, we can see that delta S by delta T is equal to R by V delta V by delta T. And this is change in velocity with respect to time, which is nothing but the centripetal acceleration that we are trying to prove. And this change in displacement with respect to time is nothing but the V component, that is already the tangential component of the velocity. So we can derive that acceleration centripetal is equal to V square by R, and this is acting towards the center of the circle. So acceleration will always act toward the center of the circle and is responsible for the direction change of the velocity. So that's it. So we can prove that centripetal acceleration is equal to V square by R. Thank you.